and it is actually about the checking of the model, diaphragm assignment, uh, assignment of loads to structural members, selection of the design code, and the analysis of model and checking of different results. For example, the check that will perform dual system requirement, that your system is dual system or not. The checking of the model is very important. So before assignment of the loads or running the analysis, so this check should be performed, and it checks what? It checks the model errors for the joint connectivity. When the joints are not connected properly, then it will give you error that these joints have issues. And the next will be the shell overlapping. If you have model shells 2 times in a grid, so it will specify that shell name to you that these shells are overlapping, then you have to delete that overlapping. Frame connectivity issue, that the frames are not connected properly, and frames overlapping, that, for example, two beams you have drawn model two beams at the same grid. So before running the model, there should be no error. So your analysis will not take time. So when there is an error, it will give you information about the error, that this error can be removed. For example, it will give the warning, and it will say the model has been checked and one warning message. And it will say the ground floor F87 and F7 are too close. It means they are overlapping. So then you have to check for those frames, and then you have to remove that error before you run the model. How you can check that? You have to go to, I think all of you would know this, but let me go to this. You can click on this analyze and click on this check model and select all and click OK. So if there is error in the model, so it will identify that these are the errors, so you can remove. So if there is no error, it will give you the warning that the model has been checked and no error has been found. Normally, I don't do this in the model on live meeting because it takes a lot of time, right? So it has been checked, and the model has been checked and no warning message was generated. So let me overlap a beam. For example, this grid, this is the first floor. Let me draw this, for example, let me draw this beam again. And now again, check the model. So there should be an error that these two beams are overlapping. And when there is error on that floor, so it will highlight those frames, those slabs. It's checking, let me check it. Because it hasn't drawn this one, let me delete this. So it was not drawn. Somehow, this is actually demonstration. It takes a lot of time, so we will move on. This type of error will appear, and you will face these errors, so you have to check those errors. Next is the diaphragm assignment, and the diaphragm must be assigned to the shells. horizontal members. In order to transfer the dynamic loads, the forces, it is actually work as a collector. It collect the loads, transfer it to the frame, which is the beams. Slab transfer the forces to the beams, and beam transfer it to the columns, and from the columns it has been transferred to the foundation. So there are two types of diaphragms. The first one is the rigid diaphragms. Concrete slab is taken as always as rigid diaphragms. The discs, that is composite beams design, when the depth of the slab is greater than more than 3 inches. Actually, the rigid diaphragm do not incorporate the shear deformation. If you want to design your slab to incorporate the shear deformation, then you have to select the semi-rigid diaphragm. Because in semi-rigid diaphragms, it allows the software to incorporate the shear deformation and design it for that. But normally the concrete slab has in-plane shear, that much shear capacity that it does not require any shear reinforcement. But in case of the beams and slab columns, it requires shear reinforcement. So semi-rigid diaphragms is you can take as you are designing steel discs which have no composite beams, only simple steel and steel plates. Wooden slabs, hollow slabs, you can take the diaphragm top as a semi-rigid diaphragm. So we will go to the ETAB and we will define the diaphragm type. We will go to the define diaphragm, and we will add new diaphragm, and we will name it as rigid. And we will select rigid. You can select semi-rigid or rigid, click OK, and OK. Since we have all floors have same floors, means there is no steel discs, no wooden slabs, no hollow slabs. So all of the floors have the same property. So we'll assign the same diaphragm to all the floors. And we will select object type, not object type. We will select property, slab section, and select slab 6.5. Select and go to the assign shell diaphragm and apply rigid. You can see that rigid diaphragm has been assigned. So Bismillah ar-Rahman ar-Rahim. Let us start our classes again. We have studied the module 4 up to the diaphragm assignment, and next is the assignment of loads to the structural members, and the loads will be superimposed dead loads. So these loads are actually applied on your structure as per the occupancy of the building and as per the requirement. And for the design routine practice, we name it as SDL, which is the super dead load. And normally we take as 30 PSF for 3 inches for tiles on all type of floors. And its calculation is very easy. For 3 inches, you have to know about the density, and we normally take it as 120 PCF. And you can calculate the area load by multiplying the thickness to density, and you will get the area load. So we will take 30 PSF load as the tile marble load. Next is the partition wall loads and brick wall loads, and it is normally taken as the load per running foot if the walls are resting on the directly on the beams. But when the walls are resting directly on the slab, then you have to take the area load. So in the routine design practice, this load is normally taken as the area load, and you can calculate the area load for any type of the building. Just you have to know about the height of the walls, length, and thickness of the wall. For example, in the high-rise building, the partition walls are normally 4.5 inches. And if you take the density is 120 PCF, so load per foot will be 120 into 4.5 divided by 12 to convert into feet, and take the height is 11 feet. So you will get 495 pound per foot. So now should you be able to calculate the running foot load for any type of the material. So if the walls are resting directly on the beams, so you can take the loads per running foot. But when the walls are not resting directly on the beams, then the area loads for the brick should be applied on the slab. And the formula for that to calculate the area load is that you have to multiply with the density, height, thickness, and length of the walls, and then you have to divide that with the slab panel. So for example, the typical, if you take the apartments, so normally you will get a length of approximately 70 feet to 80 feet or 60 feet to 70 feet. So we have taken as 70 feet. So we can calculate the area load as the following, that 120 into 70 into 11. I have taken the height of the wall is 11 feet and the thickness is 4.5 inches, and we will get total weight of this much pound. And if you take the panel in which our building is 25 cross 20, so you will get the area load as 69.3 PSF. So you can take it as 70 PSF. So the total load will become 69.3 plus 30. It will become 99.3 PSF. So we will take 100 PSF load as SDL on all floors except corridors, roofs, and restaurants. So for the roofs, we will take it as a 30 PSF only for the tiles and marbles. On the restaurants, we will take 30 PSF for the tiles and marbles and 20 for the other furnitures. And for the corridors, we will take only 30 PSF as a superimposed dead load. These are the live loads. So first we will apply these load. Actually, this was not an actual architecture drawings, but you can specify the corridors, which I have done it, and you can color it with different, you can name it with different colors. For example, if you right click on this corridor, I have named it as a corridor, but the thickness of this slab will be same as that of the normal slab, 6.5. So just for the understanding and for the learning purpose, I have taken these path as a corridor, and these will be the lobbies. So the load for the corridors and the lobbies, the live loads and the SD loads will be the same for the corridors as well as for the lobbies. You can see that for understanding purposes, I have added these paths as the corridors and lobbies. So now we will apply the dead load. So we will hide the walls. And we will also select the corridors. And right click and hide the selected objects. So we do not want to apply the 100 PSF load on these. So we will select this floor. This is actually, let me open the architecture. So the roof, restaurants, and corridors, which corridors we have hide these corridors. For the roof and the restaurants, we will apply 50 PSF. And for the roof, we will apply 30 PSF. And let us open that. So this is the parking. We will apply the parking load on the raft. This is actually the slab that will be the offices, and we will apply 100 on this floor, and that is from the ground floor to 5th floor. We will select this one. Actually, we will select all the floors, and then at the end we will apply different loads on the restaurants and corridors. You can select it one by one. Click on the assign shell loads uniform. Click on the SDL and apply 100 PSF load on that. Right? So you have applied the 100 PSF load on all the floors. So now we will set 8 different load on the roof, restaurants, and corridors. So now we will go to the 18th floor, which is the roof, uncheck the all stories, select only these, and apply 30 PSF and replace the existing load. Click on apply, right? So 30 is applied here and 100 will be in the lower story. Now the restaurant is on which floor? This is the 6th floor. We will go to plan, 6th floor. And now we will select again these floors and we will apply 50 PSF load on the restaurant. And you can see that here it is 50 is displayed and it is showing you that uniform gravity loads in SDL 50 is applied. And in the lower story, it is 100. So for the roof, we have applied this. For the restaurant, we have applied 50. And for the corridors, now we will invert the visibility of the objects, right? So you can see that it has been applied at 30 and 100. So you can select the property slab section, corridors, and apply an SDL of 30 and click on apply. Now you can see that, let me show all the objects, that in the corridors and the lobbies, the load SDL has been applied 30, and for the rest of the slab, it is 100. Similarly, for the roofs, this is the same case. You can also, you can see that for the roof, there is no corridors, which is actually a flat roof. So the load should be the same. You can see that for the slab, as well as for the corridors and lobbies, the load has taken as same as 30 PSF load. Next is the live loads, and live loads can be selected from the C716 table 4.3-1. And I have extracted the main uniform loads from that table. And we have concluded that for the office use, you can take the uniform load PSF is 50 PSF, and for the kilonewton per meter square, you can take is 2.4. So for the office, we will take 50 PSF. For the restaurants, we will take 100 PSF, right? So these are the dining rooms and restaurants. You can take 100. For the apartments, we will take 40 PSF. And for the lobbies and corridors, we will take 100 PSF live. And for the roof, you can see that roof's ordinary freight roofs, curved roofs, you can take as 20 PSF live load. And for the assembly areas, for example, fixed seats and lobbies, you can take 100 PSF. And for the corridors, it is the same values as first floor and same as occupancy, or you can take it on the conservative side as 100 PSF. So now we will go to the ETAB and we will go to the first floor level and we will select 6 stories because it is from the ground to 5th floor. It means total 6 stories. And that will be 4th and that will be 5th. Now click on the live and apply 50 PSF live, right? And you can see that the live load has been applied on corridors as well. So better to hide the corridors. Again, select the property slab section, click on the corridors and hide these slabs. So later on, you can apply 100 PSF live load on these slab panels. So the office load has been applied. The 6th one is the restaurant, and it is 100 PSF. You can apply 100 PSF, which is the 6th floor. Next is the 7th to 10th floor is apartments, and again we have apartments. So from 7th floor onward, you can apply 40 PSF live load on your floors, except roof, which is the 18th floor. You can select it that at once, but let me do it manually one by one. This is the last one, and apply 40 PSF live load. And for the roof, you can select the roof and you can apply the live load of 20 live. Now again, invert the visibility and select the slab section corridor. And for the corridors, the slab, the live load is same, which is the 100 PSF, except the roof, because the roof will have 20 PSF as compared to the remaining floors. So you can see that for the other slab panels, it is 40, and for the lobbies and corridors, it has been taken as 100 PSF live load. For the live load for the parking area, for the ramp, you can select or you can take the 60 PSF live load on the slab panel, on the ramp, or on the raft. So on the raft, you will take 100 PSF live load for the vehicles, and you will also take 30 PSF for 3 inches PCC when we are modeling the raft. So we will go to the building view limits, and we will only display 2. Click on the 3D, and we will select this ramp, and we'll go to assign, shell loads, uniform, and it weighs 60 PSF. Normally, the slab concrete is used as the finished surface for the ramp, so there is no need to take the 30 PSF load on the ramp. If the architect wishes to use tough tiles or any other material on the ramp, then you can take the load accordingly. The loads on the retaining wall, that these loads must be applied, and you can ignore these loads in such conditions when you are not designing your structure for the seismic, but we have also excluded these walls from our seismic ranges because we applied the load at the top of the retaining wall. So you cannot take the retaining wall load as an SDL that we have defined previously. So you have to define a separate load pattern for the retaining wall loads, which is the soil. And you have to take the load only in that case when you have a passive type of soil, that it means that it is very loose and there is a possibility that the soil will apply load on the retaining wall. The soil on the soil that are which are very hard, for example, the gravels and the hard rocks, so they are normally at rest. So there is no need to take the load for the soil which are at rest. So in order to take the load in the ETAB, you should know the height of the retaining wall, the density of the soil. You will get it from the soil report. And this is the equation that is used in the application of the trapezoidal load, triangular loads. And if you do not have any loads, for example, the actual equation is the P, which is the pressure, AX plus BY plus CZ plus D. And these are the different coefficients in different directions. So we do not have any pressure coefficients in the X or Y direction. So these two will become 0. So you are left with the equation P is equal to CZ plus D, and Z is the depth, D is the constant, and C is the coefficient of the Z component. So if you see this diagram, this is the retaining wall and this is the soil pressure. If it is passive pressure, then you have to take this load in the ETAB. Otherwise, you can ignore this load. So this is the base of the retaining wall. This is the top of the retaining wall. So at the base, the Z, what I'm talking is the terminologies of the ETAB, that it takes Z as 0 and pressure is maximum. And at the top of the retaining wall, the pressure is 0 and the Z is 12 feet. So if you put on these values in this equation, when Z is 0, which is the base, so P will become 12 into 120 into, which is the density, and this is the height. So it will become 1440 PSF. So the equation will become D is equal to P is equal to 1440 PSF at the base. So this much pressure is applied at the base of the retaining wall. And when the Z is 12 feet, at the top, the P is 0 PSF, equation becomes C into 12 plus 144. You have to insert the value of D, and the C value become minus 120 PSF at the top. So this is how you can apply the soil loads or triangular loads in the ETAB. So we will go to the ETAB and we will go to the define, and we will define a soil pressure, and we will add it as other, right? And we will add the soil pressure. This is okay. Now let me show the walls. Remove all of these. This is the retaining wall. Select property wall sections and select retaining wall and click on the show selected object only, that is invert visibilities. Show all. Let me hide it from here. So this is the retaining wall. You have to select the retaining wall, go to the assign shell loads and click on this non-uniform load. And you have to select the load pattern, which is the soil pressure. The direction is in which direction you want to apply the load. We'll go to the direction and we will check the direction, other shell local axis. And you can see that these are the local axes for your shell. This is the red one is the X direction. The green one is the Y direction, direction 2, and the blue one is the direction 3. Local axis 3. The red one is the local axis 1. The green is local axis 2, and the blue one is the local axis 3. So we are interested in the local axis 3. So you can see that the direction is outward. We want that direction to be inward towards the retaining wall because the soil will apply the pressure towards the basement. So we will select, this is okay. We will select this one and we will go to assign shell and click on the local axis and rotate. The default orientation is 90. Click on apply. This one. Right, is inward, so you have to apply it 180 minus 180. Assembly local axis default orientation, it is 90, it is 0, so that will be default. I want to rotate it by 180 degree. I don't know why it's not rotating the local 3 axis. I don't know why it's not rotating the local 3 axis. All right, so you can also apply the load when the local axis is outward. You have to only apply the negative and the positive signs to the values. For example, these two are towards the basement, and I will check it why it's not rotating the local 3 axis, and then I will share the information. So these are towards the basement, so you can apply the loads that we have calculated. Click on the shell loads non-uniform, click on the soil pressure, and click on the local 3 axis, right? So local 3 axis is actually towards the basement, and these two coefficients are 0. C is minus 120, and this D is 1440, right? So click on apply. So these loads will be applied towards the basement wall. And the next, which I have tried to invert the direction, click this. This is outward. The thing you have to do is to take it as positive and take this as negative. So the loads will be applied if I right click on it. So you can see that the load has been applied, which is the load pattern soil pressure, and it is non-uniform in the direction of the local 3-axis. Next is the overhead water tank loads, and normally we do not take the lateral loads on the overhead water tank, but just like the retaining wall, you can define your own load pattern for the water. But the main important thing is that you take the weight of the water in the seismic weight of the building. So for that, you have to apply the water load, which is the gravity load on the bottom of the underground water tank. So you can calculate for the height of 6 feet, the density of the water is 62.4 psf. And when you multiply it with the 6 feet, you will get 375 psf live load. And you can design the walls separate in the separate model. We go to the views, building limits, select view all. We will go to the hero tank bottom. Let me show the floors. Click this and assign the shell loads. It will be as a live load. So it will be 375 in the gravity direction. And if you want to add some tiles or marble, not normally added as PCC. So you can take for the PCC load as 30 PSF as well on the underground water tank slab. If you right click on it, you can check the live load and the SDL. So this was the whole story about the loads that you can apply. The loads application may be different for different building. For example, for the hospital, it will be different. For the apartments and for the only offices, it will be different. And you have seen it for the gyms, and for the other occupancy types, the load may vary. And then you have to select the desired code for which you want to design. For example, the American code ACI 31819, Chinese code, British code, Europe code, Hong Kong, and as per your location of the proposed building. So you can select the code from the design, concrete frame design, and click on the view preferences. And you can select the design code from here. And the code ETABS will define the load combination and perform different checks on the structure elements as per the design code selected. So you select the ACA 31819, click OK. And then you have to run the model, right? And you have to perform different checks. For example, I have run this model because we cannot run it live. It will take time. So you can check, for example, the deform shape of the building. For example, in the earthquake, I'm not going to explain it further. You can see that it has been shown as deform shape. In the gravity direction, you can also check. And many other elements, you can check it out. There is an important command, which is a section cut, and which is used for the different forces to be checked in these structure elements. And you can define it from define menu that what forces you want to check for the analysis forces, or you want to check the design forces. You can go to the define section cuts, add section cut. And from here, you can select if you want to section cut a group of all, or you want to select a specific group of elements, or you want to check the forces for the analysis, which is F1, F2, or you want to check the section, the force for the design purposes. So we'll click on the analysis because we want to check the forces for the analysis. We click OK, right? And then you have to run the analysis. So after you have run the analysis, you click on the 3D, right? So what I'm doing is that we are checking actually the dual system check. And for that, we will use the section cut. So for the dual system check, because we have discussed this, the 25% is must for the frame. Then you have to display the shear forces in the 3D view corresponding to the EQX or EQY, and draw the section cut above the basement slab level in order to check the percentage of the walls, that how much it has taken the seismic forces. Click on the 3D and then go to the view, set the 3D view and make this elevation and aperture 0, 0. Click OK. Now this is a 3D view, but in elevated form. Go to the draw. You can see that you cannot draw the section cut as long as you haven't shown any forces. Click on the display frame forces, click on the EQX and click on the shear, apply. Right, now go to the draw, section cut, and cut the section above the retaining wall, and it will display forces. These are the integrated forces. This is the force in the X direction, this is in the Y, and this is in the Z. You can see the load case earthquake X is selected, and all the members has been selected. The total force is 6961 kip. And if I uncheck the walls and click on the fresh, so you will get the FX value. For example, the 1089 kip of the earthquake forces in the columns. And for example, if I check on the only walls, so the 5873, for example, this is actually a typical example that you can check it out, the dual system check. If I click on the Y direction, and again click on the draw, section cut the section above the retaining wall, you will get the total value of 6961. And for the columns, uncheck the walls, and you will get the value of 2036 for the columns, right? So it may actually, I have added a few things, so the values may vary from the live checking of the model, or if I have added in the PowerPoints. So this is actually the method which I'm trying to teach you, that how you can check the forces registered by the columns only and the forces registered by the walls only. If you want to check the forces registered by the walls in the Y direction, the seismic forces, so that will be 4924 in the Y direction, and for just for the columns, it is 2036.6 kips. So you have to extract these values, and then you have to add these as an input in the Excel sheet, and it will give you the percentages that the system is dual system or not, right? So this is the whole procedure. You can do it by yourself. Let me go to the presentation. For the dual system check, uncheck the walls to get the forces resisted by the columns, which I have shown you, that the total load resisted by the walls plus column is 6990. And if you uncheck the columns, so the walls, so the column forces is 2245 kips, and the forces resisted by walls is 4745. So you have to insert these three values in the Excel sheet. So this is the Excel sheet, right? So you have to insert these values. For example, it is, let's say, 7,000. You have to insert this, let's say, 3,000, and this is 2,500. So it will give you the percentage that how much forces per in percent resisted by the columns in the X direction and the Y direction. For example, it is 1,000. So it is less than 25%. So it will give you remarks that revise your system. And in the Y direction, it is, for example, it is 500. Again, it will give you indication that your system is not okay. It is not, the frame is not resisting 25%. So you have to revise the system. So this is for the X direction, right? This is the total. And if you uncheck the walls, so this is the X direction forces by the columns. Similarly, for the Y direction, the total force is 6990. Again, it is same as the X direction. And if you uncheck the walls, the load resisted by the columns in the Y direction is 2736 kP. Right? So you have to insert these values in the Excel sheet, and it will give you the percentages. For in our model, the system in X direction is okay, and in the Y direction, because we have 6990, and the forces resisted by the columns in the X direction is 2245, which is 32%, system is okay, and in the Y direction is 39%, system is okay. So if the forces resisted by the columns in the door system is less than 25%, then you have to revise the frame structure and what are the different strategies that we have to adopt. We can increase the number of columns, or increase the FC prime of the columns, or increase the size of the column, etc. And this remarks will appear that we have to revise the system. So this was the whole story about how you can check the dual system, or you can apply the loads on your building. Let me turn off this presentation.